Today we're going to begin our discussion about exploring data using tables and graphs, talking about frequency distributions and using those to summarize data. So the big idea here is when we have large data sets, a frequency distribution or a frequency table can help us organize and summarize the data. That way we don't have just random numbers floating all over the place, which is the format that data comes to us in a lot of times. So a frequency distribution can help us understand the basic setup of the data, the distribution of it, what it looks like. So a frequency distribution or frequency table, it shows how data is partitioned among several different categories or classes by listing those categories along with the number of occurrences of data values in that category. So let's go through a few definitions that we need to be able to create a frequency distribution. The first is the idea of a lower class limit. This is the smallest number that can belong to a class. So when we put all of them together, it's the smallest numbers, it's all of the smallest numbers that can belong to each of the different classes that we make. If there's a lower class limit, there's also an upper class limit, and it's just the largest number that class can have, or when we put all of them together, they're the largest numbers that can belong in each of the different classes that we make. And finally, we have this idea of class boundaries. Now, class boundaries is something that we would communicate to somebody as like the dividing point between two different classes. Now, it would seem like that should be a lower or upper limit, probably, as you think about that at first. The thing about the lower and the upper limits is the lower limit, there can be values that are the lower limit in a class. And the upper limit, there can be values that are that upper limit in the class. So if we actually made the upper or lower limit the boundary, then there would be values that fall into more than one class, and that's not okay. So what we do is we take the lower and the upper class limits, and we choose a value between them. So we might never have a data point. In fact, we won't have a data point that hits that boundary value. So say all of our values have to be whole numbers, so no decimal points allowed. Well, then our lower and upper class limits, those will be whole numbers. So there will be a gap of 1 between an upper class limit and the next lower class limit. The class boundary could be the 0.5 in between, halfway in between those two values. So these class boundaries are the numbers that we use to separate the classes, but they don't allow those gaps the way our class limits do. Now, there are two more definitions that we need to think about, but they're not as central maybe when we're looking at our classes. The first is the midpoint. This is the middle value of each class. So we find that by taking the upper and lower limits, adding them together and dividing by 2, and that'll tell us where the middle of the class is. The second one, which we'll use to decide about making our frequency distribution, is a class width. The class width is the difference between two consecutive lower class limits. Right? It's also really tempting here to take the upper minus the lower and say that's the width. But if you think about it, we're looking for, say, the distance between the number 2 and 4. We do 4 minus 2, and we get 2. But in our class, the numbers 2, 3, and 4 were all allowed to be there, so we actually should have 3. So that's why we take the 2 lower class limits, and that shows us the entirety, how many different values, data values, can be in that single class. That's our class width. So now that we have these definitions, let's talk a little bit about how we would construct a frequency distribution. The first thing we would do is choose the number of classes we're going to have. The way you choose the number of classes can depend on how spread out the data is, how many data values you have, the context of what you're studying. There are a lot of things that can go into deciding the number of classes. Usually, the number of classes you're going to want is going to be between 5 and 20. Once you know the number of classes, then you can use that to calculate the class width. The class width is going to be about the maximum data value that you have minus the minimum data value that you have divided by the number of classes. The reason we say it's about and not exactly equal to is because if we make it exactly equal to, sometimes we end up with really weird width classes with decimal places where they don't make any sense and stuff like that. So what we do instead is we take this difference and then the quotient by dividing by the number of classes from the difference. And then we're going to take that resulting number and we're going to round it up to something that makes sense. Sometimes it's the next whole number, and sometimes we say, I'd really rather be working with a multiple of 5 or 10, and it makes sense to round it up that much. So we're going to round this up to get a convenient number, whatever convenient number might mean in the context that we're given. Then, after we have our class width, we're going to choose the value for the first lower class limit. We can either use the minimum value of our data points, or we can use, again, a convenient value that's less than that minimum value. This idea, again, convenient value is going to depend. If we're really close to 0, we might want to start at 0, or we might want to start at a multiple of 5 or 10. Along the way. Again, it's really whatever makes sense given the context and the data set that you have. Once we've chosen that first lower class limit, we're going to use that and our class width, and we're going to be able to then list all the other lower class limits. We'll do that by adding the class width to that lowest lower class limit, and then adding the class width to the result of that, and to the result of that, and all of these different sums that we get along the way are going to be giving us the next lower class limit. Once we have all of our lower class limits, then we're going to list those out in a vertical column. We'll put a little hyphen next to each one of them. And then we'll list the upper class limit, which will just always be one less than the lower class limit of the limit after it. So if our lower class limits are at multiples of 10, then our upper class limits will always end in 9, because the next one would be the next lower class limit, the next multiple of 10. Then once we have all of these ranges listed out vertically, what we're going to do is take all of our data values that were given, data points that were given, and we're going to put a tally mark in the appropriate class and basically just sort them all out into what class they fall into. And then we'll count up our tally marks, and that gives us the frequency. So let's take a look at an example. This is McDonald's lunch service times. All right, so we have a set of data. It's the drive-through service time in seconds for McDonald's lunches. All right. We're asked to make a frequency distribution using 5 classes. So we're going to, step 1, 5 is our desired number of classes. That was told to us, so we're done step 1. Step 2 then says that we need to calculate the class width. So 5 is the number of classes we have. So we need to find our maximum data value. And we see that is 308 if we look at these. And then we need to find the minimum data value. So looking through our data, we find 83 to be our smallest data value. So we're going to go through and we'll do our maximum data value, so 308, minus our minimum data value, or 83, and then we're going to divide by the number of classes. When we do this, we get 45, which is a fairly nice round number. But since it's fairly spread out, our data between 308 and 83, and 45 is nice, but it would be even nicer if it was a multiple of 10. We're going to round it to 50. So we round 45 up to 50 for an even more convenient number to work with. And then we're ready for step 3. So our minimum data value, remember, was 83. It's really not a very nice starting number. It's not a multiple of 5, not a multiple of 10. So we are going to go down to a value that's nicer to start at, right? You could go down to 80. That would be all right, right? But adding 80 plus 50, we don't necessarily think about adding 50 to multiples that aren't like multiples of 25. And so it's more convenient a lot of times maybe to go to 75. This is, again, a very like your choice type of thing. All right. So going from 45 to 50, that's what you're comfortable with and what makes sense to you. All right. That's a choice that might be different for different people. And so is going to 75 instead of, say, going to 80. All right. Staying at 83 is maybe not the best choice, but either of those other options is pretty good. All right. So once we've decided where we're going to have our lowest lower class limit, we're going to choose 75 here. We're going to add our class width to that. So 75 plus 50 gives me 125. That's my next lowest class limit. Then I'll take 125 and add 50 to that and get 175. I'll take 175 and add 50 to get 225. And I'll take 225 and add 50 to get 275. I said there were going to be 5 classes, and 75, 125, 175, 225, and 275 are 5 lower class limits, so I can be done coming up with my list of lower class limits. Which means I'm ready for step 5. Step 5 says that I'm going to list those lower class limits vertically, and there they are. I put the little hyphen next to each one of them so I can determine the upper class limits. So since 75 goes up until the next class, and the next class starts at 125, the upper class limit for my first class needs to be 124. Similarly, my next upper limit needs to be 174, and then 224, and then 274. And finally, 324. So I end up with all of my lower and upper class limits listed vertically. And then I'm going to go back to my data and I'll make tally marks. So 83 falls into my first class. I'd make a tally mark there. I have something like 123 that also falls into the first category or first class. I'd make another tally mark there. And I'm going to repeat this for all of my data points, and then at the end, count up my tally marks. And if you do that with this data set, this is the frequency table or frequency distribution that we get. Now, a frequency distribution like this, we can very easily look at it and say, you know what, it doesn't look very common to have 225 and above seconds waiting for our lunch at McDonald's. And it's most common that we're going to wait between 125 and 174 seconds. But that 24, the actual frequency itself, what it means to us, it's hard to get a really great grasp of that sometimes. So that's where this idea of a relative frequency distribution comes in to help us out. A relative frequency distribution or percentage frequency distribution, what it does is it takes all those raw numbers that might not mean a ton that are our frequency counts, in our frequency distribution, and it changes them into percents. So the classes stay the same, and the frequencies, what we do is we take the frequency for the class and we divide it by the sum of all the frequencies, or the total number of data points that we had. And when we do that, we get a decimal that if we multiply times 100%, it gives us the relative frequency, the percentage frequency for a class. And then what we can do is we can say, now I know that 23% of the time it's going to take between 125 and 174 seconds, right? That was just an example. I didn't actually do the division to know that that's accurate. All right, so don't hold me to that. But when we say that we know that it's true like 25% of the time, that means something more to us maybe than that raw number. So when we do this, what we're going to end up with is the sum of all of these things will always be really close to 100%. I say really close because sometimes you'll have, when you do these division things, you'll have it come up to like something 0.4, something 0.4, something 0.4 a whole lot of times, and all of those you're going to round down, which will mean that you'll come up a little bit short of 100%. And the same thing could happen that we're rounding up more often, so we come up a little bit above 100%. Some people choose to make sure it always adds up to 100%. And again, this is a little bit of a personal choice thing here as well, and depending on the context. All right. So finally, cumulative frequency distributions. Cumulative frequency distributions are basically the idea that you want to know, well, how many of them are less than this value. Think about if you want to know how long it's going to take you to get your lunch at McDonald's. You might want to know, well, like, how likely am I to spend less than this amount of time? You don't really care if it's faster. You care if it takes longer. And a cumulative frequency distribution is what tells you that. All right. So what we do for this is we change all of our classes to be less than the lower limit of the class after it. So less than 125 for the class that used to go up to 124. And then less than 175 for the class that used to go up to 174. And then what we do is, instead of having 11 and then 24 as our frequencies, we have 11 still, but our next one, we take our 24 that we had and we add 11 to it, saying 35 of our data points are less than 175. All right. So let's talk a little bit about how we can use these frequency distributions to help us understand data. One of the things that we're really interested in a lot of times is if our data has a normal distribution. A normal distribution looks kind of like a bell. And so what that means for us is that we have low frequencies on the extremes, and then like in the middle classes, we get bigger frequencies, but those ones on the ends, we get lower frequencies. All right. The distribution also has to be pretty symmetric. So if I have one class that's really low on one side and two classes that are really low on the other side, and then they go up, it's a little bit not symmetric. So it's maybe not normal that way either. With a frequency distribution, we can only give an idea if it's normal. We can't know for sure that it is. So this is really just a ballparking eyeballing idea. The other thing that we definitely can tell is if there's gaps. If there's big gaps in our data, those will show up in our frequency distribution. They show up in us having classes where we actually have zeros. So gaps tell us stuff. Whenever you have a gap in your data, you should be asking, why is that gap there? A lot of times it means that there's two or more populations that are getting measured and they're getting lumped together in our data set. That's not always the case. Sometimes there's some other underlying thing and we think that they're the same population. And it's really important to know, though, if we have two populations and take data on each of them, we're not guaranteed that there will be a gap. Sometimes the two populations actually have the same, more or less, distribution. So let's take a look at this. This is our weights of pennies. So we randomly take some pennies and we weigh them. And we look at this data and we say, there's a big gap there. In the class that's 2.6 to 2.69, 2.7 to 2.79, 2.8 and 2 to 2.89, there's no pennies in any of those. That gap, that means something. So why are there a lot of pennies that are light and a lot of pennies that are heavy and none in the middle? Well, if we look into it a little bit more, we start saying, well, why would this gap exist? Why do we have light and heavy pennies but nothing in between? Then what we find is that there's two different populations there. In 1983, the US Mint changed the composition of pennies, and consequently, we got two different weight pennies to be working with. Another thing when we're looking at these things is we can do comparisons, right? Frequency distributions without using the relative frequency, it's a little bit misleading sometimes to use them to compare, but relative frequencies make it apples to apples. It doesn't matter how many pieces of data we had from each of the data sets that we're looking at and trying to compare, because percentages don't care. The percentage normalized for that, accounted for that already. So let's say we wanted to compare how long it takes us to get our lunch at McDonald's or Dunkin' Donuts. All right, so McDonald's, we see the relative frequency distribution there. In Dunkin' Donuts, we see their relative frequency distribution. Now, if I saw either one of these separately, we saw the McDonald's one and it said, oh, and it looked like, oh yeah, McDonald's is pretty quick. And seeing Dunkin' Donuts separately, you'd say they're pretty quick too. But it's not until you put them on the same frequency distribution where we can see the classes to see that Dunkin' Donuts is actually deserving of a class that's even faster than McDonald's fastest class. And McDonald's has two classes that are longer or slower than Dunkin' Donuts' slowest class. And so then we look at this and we say, oh yes, Dunkin' Donuts is definitely a faster place to get lunch most of the time.